Hello and welcome. In my various amplifier design and configuration videos, I analyzed power consumption and power delivery. I looked at RC snapper technologies and created various circuits on a PCB board. The challenge today is, can a zero voltage switching dual class C amplifier consume less power than a class C amplifier for the same voltage output of a flyback transformer? Let me explain in more details. We want to drive a flyback transformer to achieve 18.1 kV on the secondary coil peak to peak. The class C amplifier has one MOSFET and uses only the positive wave signal on of the gate. It switches off on the negative gate signal. My design zero voltage switching device is a dual class C amplifier which receives each of the signals from a sender tapped signal transformer with very high fidelity based on nanocrystal technology. We have twice the components we need to energize. My question again is, can we consume less power than a single class C amplifier to achieve 18.1 kV on a secondary on the flyback transformer? At first, you would say that is impossible. I cannot have more power consumers and use less power than a device which has as half the number of components. If we look at the goal we want to achieve, we need to look at the characteristics of the wave. Let us compare it to a swing on the playground. You stand behind the swing and push and wait until the swing reaches you again at the highest point on the back, then you push again. The result in the elevation level requires power, but you can only be provided at 50% of the time. This means you require more power to push to achieve that. Now, the ZVS dual class C amplifier can be compared to two people, one on each side of the swing. Each person pushes a little until the elevation level is the same as for the single person. The power each person must use is less for only one person. The power required should logically be the same. However, there are losses for the waiting of the single person until it can push again. These losses are cut by half for two people which do not need to wait. In general, we can say we have with a half-bridge less losses, but for that to take effect, the design must be very efficient. Compared to bootstrap technology, my ZVS design does not require a very tight component selection for DC bias and bootstrap capacitor, which operates only at one frequency, one voltage and one current level. Now let us have a look at the demonstration table and the PCB boards I use for my test today. Here on the demonstration table you see now the two PCB boards for the test. Currently I have connected the single class C amplifier to the load. So we have to the load that you can see here in red also an inductor. The inductor is required to smooth the wave. It works as a kind of a filter and also as a storage device, which allows us to have a smooth transition of power to the primary coil of the flyback transformer, and therefore we have a better transition to the secondary, which means we have a clean wave signal available which we can measure on the oscilloscope. So technically what you see here on the left side, the class C amplifier with one amplifier, we have on the right side exactly twice of it next to each connected. They are linked to each other from the power rail point of view, but from a construction or from a component point of view, they are identical, but only twice as many. So we'll go over now to the demonstration table, and I will start with the experiment. So I'm now at the demonstration table here again. Here is our single class C. I have now put into the picture, you see then the oscilloscope as well. You see the power supply we're going to have here. At the moment it's 5 volt here on the driver and 5 volt on output, and I have it currently at 16 kilowatt as a starting point. So we measure then from the output here via the high voltage probe on via the oscilloscope. So I energize this now, and you see at first we see the signal here. We see the signal which comes in exactly 16 kilohertz, and if I energize that now, we have a wave of currently 6 kilovolt, and you know the process as used, we are tuned for the highest values. That's what we normally always do. If that's the right thing or the wrong thing, it's a different subject. I will not go into that today. But if we have that like that, we are here. Let's put it that way. 18 kilohertz. And now I'm increasing. Let me focus on, we have it currently on the channel 2. And I'm gonna increase now the voltage until I achieve 18.1 kilovolt. So here I'm at 18.1 kilovolt and I measure 4.57 watt. So 4.57 watt is this, and you see here's a small ripple. So what I didn't talk about is, I had it in the last video, I have a small smoothing capacitor, it's a gate capacitor which I indicate. I have also the RC snapper circuit which I don't use today. I use a gate smoothing gate capacitor which allows for very, very small ripple. But it is not only the gate capacitor which does that, it is also the inductor which reduces the ringing coming back as a back EMF from the high voltage transformer via the primary. So the inductor is important and we should use it to reduce all the kind of disturbances and back EMF issues, specifically here with a flyback transformer. So we take a note of this value. Probably have to go a little bit lower. 18.1 kilovolt here again. So 4.4 watt. That is my last reading. We take a note of that, and I will now move over to the dual ZVS Class C half-bridge amplifier. I have now connected all the wiring to my dual Class C amplifier, and you see here in the corner, you see here, this is my signal splitter with a nanoperm core, nanocrystal core, which goes here in the two inputs for each Class C amplifier. Technically, as I said, they're identical. They're two Class C amplifiers. However, in this combination, you have never seen it anywhere working with. You have all kinds of half-bridge topologies, either they're PN technology or NN, and that's here in this example, it's NN, it's negative, NPN, MOSFET, both are identicals. Again, I'm using the smoothing capacitor on both sides for only the gate and not using an RC snapper, so I'm not adding an RC snapper circuitry on top of that, because I'm getting much more efficient results like that, and I take care of all the other rebels with other components outside, or I use an external regenerative device or circuitry to allow for smoothing of the signal. So we're starting that one up. I have it at 6 volt. Let's do that at the moment. And the frequency is also a little bit lower. So we have what we can see now on our oscilloscope. We see the signal, and as you can see here, voltage level on both signals are identical. Absolutely clean signal is coming in via my signal splitter, and that's what we're going to have. The frequency is a little bit lower. Instead of 18 kilohertz, I have 16.6 kilohertz, as you can see. So if I energize that up now, it's a frequency. See what you're gonna get. So we're gonna have, let's have a look. I need to add a little bit more of voltage. See what we get. (18.1 kilohertz). It's 3.42 volt, and see if we can improve of that. see if I can make some changes. .87 69. So we are at 18.9. I have to go down with the frequency, with the voltage. 18.1. What do we have? 3.28 watt. And I believe I can go even lower down. I have it in my other video last night I produced. It was down to 3 watts. See if we can achieve that again. What do we have in here? 3.18. Let's see if we can achieve even better radius. I think that is the lowest value we have. 314. 18.1 kilo. 3.18 watt. 3.18 watt is the current value I have. The lowest value I can achieve at 16.6 kilohertz. If you look at the waveform here on top and right, you see a little ringing. So this is also because it's the same. We have the smoothing capacitors on both sides for the gate, and because we use also in the center for the primary coil, we're using the inductor, which allows us to get stored energy in each cycle into the primary, and also reduce the back EMF is coming through because it works also as a filter. So we have very, very little ripple. That means it's not required to use an RC sniper circuit in this kind of configuration. And with a little smoothing capacitor, we have a very, very clean signal here without any kind of problem. And you can see here, we're measuring only 5.8 volt. And I put in currently, let me show you that. I'm putting in 5 volt only. So that is a slightly higher offset. So only 5 volt. So if I can, if we increase that here, let's say we go to 8 volt, which helps us a little bit with the transition. Power point of view, it is 97 milliwatt. Let's put it on 8 volt for the driver, right? So I now go back here. So where are we now? 3.23, but we are at higher. So if I go down now to 18.1, here we go. 18.1 kilohertz, we have 3.07. So the transition, that's another important aspect you need to think about, is there's a relationship between the gate voltage and the drain voltage. The ratio need to be ideal. Most of the time I used only 5 or 6 volt and I didn't see any big difference. But now, if going in very close testing and analysis of power consumption, I can say that if we have a higher voltage on the gate side, we are achieving actually a better current transition over to our load. And as you can see here, 3.05, 06, 07 watt we are currently consuming for 8 volt. Let's see if I can improve on that. If we go, let's say we go to 10 volt, see if that makes a difference. Exactly 10 volt, and 10 volt consumes 160 milliwatt. That is not, of course, to be considered as an additional power consumption. So if we go now on 2, here 17.8, 305, 306, we are 302. So we are in a range of 304, 305 watt. This is the lowest value we currently have available, and that does clearly prove that the tubular C as 0 voltage switching is far superior to 1 class C. Yes, we know we have 50% losses technically, because it works only 50% of the time. However, it is not really true, because when the wave is coming back, the wave coming back from the initial push from the amplifier, it is also the energy which is put in. However, this wave coming back is a lower wave or lower energy wave. That means for a Class C amplifier, we need always to put more energy in than we get out. By using two Class C amplifier working in 0 voltage switching mode, as I did it here, we can avoid this kind of losses, and therefore we have a much lower power consumption. So all the circuitries are on my website for every member. Don't need to be full members, you can be basic member. You can download that under research, diagrams and datasheets. They're all available there. And that's all for me I would like to demonstrate today. Thank you very much for watching. Until next time, and goodbye.